Okay, great. Thanks, Robert. So as you mentioned, my name is Stephen Ibanez. I'm a PhD student at Stanford University working with Professor Nick McEwen. Just to give a brief synopsis of my involvement with the P4 community, I've been spending a lot of time working closely with some folks at Xilinx in Cambridge to put together a workflow to compile P4 programs to the NetFPGA. For those of you that don't know what the NetFPGA is, that's okay. Stay tuned, because at the end of my session, I'll give a quick pitch on the P4 NetFPGA workflow. So stay tuned for coming attractions. So without further ado, let's go ahead and dive into it. So for the first 20 minutes or so, I want to spend some time explaining, giving a brief introduction to what data plane programming is and providing some motivation. So to explain what data plane programming is, let me first start off by explaining how network systems are currently built. So when you want to build a network system, you first start off with your list of requirements and all the features you want to include. And then you go and you go and look at all the available packet processing chips that are out there on the market, which all have a data sheet that specifies roughly in English how they process packets. So you go and you read all of those data sheets and you try to understand how they're working. And once you do decide on a chip, then that defines, bottoms up, how the rest of your system will be built. So it defines how the driver is written, as well as how the control plane running in the switch OS is able to interact with the data plane in the fixed function chip. And now, of course, if you want to go and add a new feature to your network, for example, add a new protocol, then you have to go and change your fixed function chip. Which can take 4 years in the best case. And after those 4 years, you've probably figured out some hack to get around your initial problem. So you don't actually need that new chip that's coming out anymore. Or if you do need it, then you have to replace all of your hardware, which is very expensive and can be a huge pain. So what P4 and this whole programmable data plane movement are trying to do is it's trying to turn this design philosophy upside down. And we do that. So what we really want to be able to do is to define at a high level exactly how packets should be processed. And we do this by writing a P4 program. And that P4 program is then compiled onto the P4 programmable devices. And in this way, we get to let network system designers define exactly which features they want to have in their network without having to let third-party chip vendors make those decisions for them. And so to motivate this a little bit more, I want to highlight a few more benefits of P4. So of course, an obvious benefit is that you can easily add new features, but you may also want to remove features that you're not using in order to reduce the complexity in your network, because so often network failures are caused by interactions between protocols that network operators sometimes don't even know they're using. And with P4 comes a much greater flexibility in terms of allocation of resources to tables. You can, whereas with fixed function chips, those allocation between tables, allocation of resources between tables, and the features are baked in at design time. And along with programmable data planes, we see much greater visibility into the network as new diagnostic techniques start to arise, such as in-band network telemetry. P4 also brings about a much more software-style development process, which enables a rapid design cycle, which enables fast innovation, and you can actually fix data plane bugs in the field. So you don't have to go and replace all of your hardware anymore. You can just change your P4 program and push that out to your devices. Additionally, since you don't have to go and talk to a third-party chip vendor to ask them to add in your brilliant new ideas into their next version of their chip, you get to keep all of your own ideas. So that allows you to obtain a competitive advantage. Another great thing about P4 is that it can be compiled to many different target devices. The Tofino is a flexible match action-based ASIC that's fully programmable by P4. Metronome has a P4 and C-based framework for programming their SmartNIC. And there's also P4 compilers for software switches, such as OpenVSwitch. And Xilinx has a P4 compiler for FPGAs, which, as I already mentioned, has been integrated into the workflow for programming the NetFPGA platform. Now, what can you do with P4? Well, there's already lots and lots and lots of interesting applications. Many of these applications have been published in high-profile conferences, such as SIGCOMM. Silk Road is a stateful layer 4 load balancer it uses the primitives exposed by P4. There's NDP, which is a low-latency congestion control algorithm for data centers, and that has a reference implementation in P4 as well. You can build a fast in-network cache for key value stores, or, as I already mentioned, in-band network telemetry, which enables unprecedented visibility into your network at a level we just didn't have before. And you could also implement Paxos if you wanted in your network, and the list goes on and on. So just some brief history about the language in P4. So it started, the ideas around programmable data planes and the name P4, which stands for Programming Protocol Independent Packet Processors. That came about in 2013, and in 2014, the first version of the language, P4.14 as it was called, came about. And that went through a number of different draft versions. And at the end of 2016, P4.16, the first draft specification of P4.16 came about. And yeah, first draft specification of P4.16 came out, and that's the version that we're going to be using today. So I just want to point out that there's this older version of the language called P4.14, and so if some of you are familiar with P4.14 and not P4.16, that's okay. There's a lot of overlap, obviously, but you'll still be able to learn a lot today. Yeah, so we'll start off with the data plane model of P4 that's provided by P4. So when we're designing a packet processing system, or when we're designing a programming language in general, it's very useful to settle on an abstraction that's convenient for expressing the algorithms that we want to implement. So P4 itself is based on a high-speed packet processing device called PISA, which stands for Protocol Independent Switch Architecture. So PISA consists of a programmable parser, which is where the user defines the headers that they'd like to recognize and their order within the packet. And then there's the stages of match action processing. And this is where the user defines the tables that they want to use in their algorithm and really defines the exact packet processing algorithm that they're trying to express. And there's also the deparser. So the deparser is responsible for putting the final headers back together to form the final packet. So the way that PISA works is quite straightforward. First, a packet will come into the programmable parser. That programmable parser will rip the headers off of that incoming packet and expose those headers to the subsequent stages of match action processing. And as the headers traverse through the match action processing stage, each stage of processing will perform, you can think of it as a transformation of these headers. So the headers can be added or removed or modified, or data can be moved between the headers and metadata and perhaps some device state. And at the end, once the final packets are presented to the deparser is responsible for putting those final headers back together to form the final packet. So parsers and controls, these are the main programmable elements of a P4 program. So these are the things that you define their functionality in P4. So parsers are implemented as a simple state machine, and their job is to extract the headers from the incoming packets. And control blocks are used to express a variety of different algorithms that can be expressed as a directed acyclic graph. So we use them to implement one or more stages of match action processing, as well as the deparser. And these parsers and controls, you define their functionality. You, as the P4 programmer, define their functionality, and they're built using the various expressions and data types that are provided in the language. On the other hand, these orange boxes listed here, the architecture description and the extern libraries, these are provided by the vendor of the P4 programmable device. So the architecture description is responsible for specifying some particular configuration of these parsers and match action tables and deparsers. So as I just presented it on the previous slide, this PISA architecture, this is one particular configuration of programmable parsers and match action pipelines and deparsers. And the vendor also provides this library of extern functions. And these externs are things that are not defined in P4, but they're provided by the vendor of a particular architecture. Oh, present looks like it's working. Okay. Yeah, so the externs are things that they're not implemented in P4, they're not expressed in P4, their functionality, but they're provided by the vendor of the particular of the P4 programmable device. And these are things that so they provide an interface such that they can be invoked by P4 programs. So the P4 programmer can think of them as black boxes. And they can often be specific to a particular P4 programmable device. So P4 makes the distinction between a target and an architecture. So a target is the embodiment of a specific hardware implementation. You can think of it as a target is as the NetFPGA platform, for instance. And then myself and the other developers of the P4 NetFPGA workflow act as the vendors of that target. So we define an architecture to expose P4 programmability of that target. So the architecture provides an interface to program a target via some set of P4 programmable devices such as parsers and controls, externs, and possibly some fixed components. So the way that it works essentially is the P4 community develops and maintains the P4 language and the library of core components that must always be present. And then the vendors provide the architecture definition, the vendor of the P4 programmable device, provide an architecture definition to expose programmability to the P4 programmer, as well as a library of externs. And so a target can support multiple architectures, and different targets may in fact support the same architecture, which enables portability of those P4 programs. So let's walk through the steps of programming a P4 target. So you, as the P4 programmer, start off with the elements that are provided by the vendor. So that's the target, the packet processing target, an architecture model to expose P4 programmability of that target, as well as the P4 compiler. So you write your P4 program to implement all of the P4 programmable elements that are used in that architecture, that is all the parsers and all the control blocks. And then you run your P4 program through the vendor's P4 compiler. And that produces a target-specific configuration binary that's used to tell the target how it should process packets in the data plane. So it includes the description of your tables and your externs. And then you, as the user, also provide the implementation of the control plane. And the control plane and the data plane are able to interact with this runtime mechanism that can add and remove table entries. It can manipulate the externs as well, and perhaps send and receive control or packets between with the data plane. So in the next session, we'll talk a lot about this runtime mechanism. So we'll leave it at that for now. So now we're going to start walking through the labs. So before we start, I just want to make sure everyone has their VM image installed. For those of you that walked in late, look for an instructor with USB sticks. They have the VM image, so you can download it. And once you have your VM image, make sure it's up to date, so just cd into the tutorials directory and then do a git pull. So the reason we're providing these VMs is because we've pre-installed a number of dependencies, which include the BMV2 software switch, the P4C reference compiler, as well as Mininet. So we'll build a network of our P4 switches and then test it out in Mininet. So each exercise directory, or each exercise is in a different directory, and each of those directories contains a Makefile that just compiles your P4 program and launches a Mininet network with your P4 switches on it and populates the table entries. Each of the directories also has a send.py and receive.py, which is very useful for sending packets. So it's just a very simple Python client and server that we'll use to send packets between the different hosts in the Mininet network. And so each of the exercises has some starter code. So read the starter code, look for the to-do comments, and that describes the functionality that you'll need to implement to complete the exercise. So this is the V1 model architecture. So this is the architecture that we'll be using today for our assignments. It's implemented on top of the BMV2 simple switch target. It consists of a programmable parser, checksum verification, ingress match action processing block. There's a traffic manager. So the traffic manager is not programmable in P4, but it performs the role of scheduling packets between the input ports and the output ports, and perhaps replicating packets as well. And then there's the checksum update and egress match action processing pipeline and a deparser. So along with the architecture description of the V1 model is also the description of the standard metadata. So this is something that's defined in the file that describes the target architecture. I just want to highlight a few of the most commonly used fields of the standard metadata. So the ingress port is set by the V1 architecture before the packet arrives at the programmable parser, and it indicates the port on which the packet arrived. The egress spec field is set within the ingress pipeline and indicates it tells the traffic manager which port that packet should be sent to. And then there's the egress port. So the egress port is read within the egress pipeline of the v1 architecture, and it indicates the port that the packet is departing from. So here's a template of a typical P4 program that's written for the v1 architecture. At the top of the file, we include core.p4. So this defines a number of common types that are used in all P4 programs, so all P4 programs should include core.p4. And then we also include v1 model.p4. So v1 model.p4 defines the v1 architecture, and as well as all the externs that you can use when you're writing P4 programs to target this architecture. And P4 programs typically start off by defining the headers that you want to include, that you want to use in your P4 program. And it builds the headers and metadata structs. So these structs are passed from block to block of the architecture as the packet propagates through the architecture. And so we define the functionality of our parser, our checksum verification block, our ingress processing block, egress processing block, checksum update block, and deparser. And finally, at the end of the program, we combine all those together and instantiate an instance of the v1 switch and call it main. So now let's take a look at the most basic example of a P4 program that I could think of. And I like to call this example the Hello World example, because it's essentially just a wire that connects port 1 to port 2. So in this simple example, the parser doesn't have to do anything. It doesn't have to extract any headers. The verified checksum block won't do anything either. And when the packet reaches the my ingress control block, it checks the port on which the packet arrives. So if it's 1, then it sets the egress spec. So it sets the port. It tells the traffic manager that this packet should be sent to port 2. And similarly, if the packet comes in on port 2, then it should be sent to port 1. So all packets that come in on port 2 will be sent to port 1, and all that come in on port 1 will be sent to port 2. And the rest of the blocks don't have to do anything. And at the end of the pipeline, or at the end of the program, we instantiate an instance of the switch called main. So with this P4 program, the routing between port 1 and port 2 is hard-coded, and we can't change it after the P4 program has been compiled and pushed out. So let's see how we can make this a little bit more flexible. So this design achieves the exact same functionality as what we just saw, but instead of using that single if-else-if statement in the ingress control logic, it defines a single table called forward, and that forward table matches based on the ingress port, so that's the same field that we were reading previously. So it matches based on the ingress port, and the actions that this table can invoke are called set egress spec as well as no action. And so the table entries will specify different value, or it'll specify which action should be invoked based on, for different values of the key, so different values of the ingress port. So these table entries say that if a packet comes in and the ingress port is 1, then invoke the set egress spec action and call that and pass the parameter 2 to that action. So the set egress spec action is defined here. We pass in the port. So this achieves the exact same functionality. And by defining our P4 program in this way, we achieve a more flexible design, because now these table entries can be added and removed by the control plane. So we have dynamic routing between the ports. So for the rest of this exercise, for the rest of this tutorial session, we'll focus our attention on trying to implement a basic IPv4 router. And we'll use this example to introduce some of the basic concepts of P4 as we go along. So our basic IP router will simply parse the Ethernet header, or Ethernet and IPv4 headers, perform a longest prefix match on the destination IPv4 address, update the source and destination MAC addresses, decrement the TTL, set the egress port, and finally deparse the headers back into the final packet. So we've written some starter code for you. It's in the basic.p4 file, so the basic directory. And this is the simple topology that we'll set up in Mininet. It's just a single triangle topology with one host attached to each switch. So for this exercise, we'll try to send a packet from 10.0.1.1 to 10.0.2.2, so from host 1 to host 2. So before we dive into the P4 programming, I just want to point out some of the types that are commonly used in P4. So an unsigned integer is called a bit string. you specify its length by specifying the end parameter. Signed integers are called bits. So with bit strings, you can perform a number of different operations, such as addition, subtraction, concatenation, and so forth. Ints support a lot of the same operations, some but not all of the same operations. P4 also supports the notion of a variable length bit string, and this is for parameters, or this is for protocols that have fields whose width is only known at runtime. For example, IPv4 options. And header types are an ordered collection of members, whose members may be one of the types that we've just discussed. Headers are byte-aligned, and they can be valid or invalid, so they have an implicit validity bit associated with them. And the P4 program can explicitly manipulate the validity bit by using the isValid, setValid, and setInvalid methods for the header. So here on the left, we show what the Ethernet header and IPv4 header might look like when we define it. And note that you can use the typedef statement to make your P4 program more readable. So some other useful types, there's the struct. So structs are very useful. And we already saw a use case of this when we showed the standard metadata for the V1 architecture. So structs are an unordered collection of members with no particular alignment restrictions. So there's 3 structs that we'll be using to build our IP router, or 3 structs that are commonly used for all P4 programs that target the V1 architecture. That's the standard metadata. There's metadata, which is where you as the user can define your own metadata fields, and this will be passed along with the packet as it propagates from block to block of the architecture. And then there's the header struct. So these are the headers of the packet that are also passed along with the packet. So a header stack is another useful type that's useful for protocols like MPLS. We have multiple headers of the same type stacked on top of each other. So it's essentially treated as an array of headers. And a header union is an alternative of one of several different types of headers. For example, you might want to declare a header union consisting of an IPv4 header and an IPv6 header if you expect all packets that pass through your switch to contain one and never both of these. So let's talk about parsers. Parsers are they're functions that map input packets to headers and metadata. So they're implemented as a state machine. They have 3 predefined states. There's the start state, the accept state, and the reject state. So it's up to the architecture to define what should happen upon reaching the reject state. For example, the packet might be dropped, or it could set some error metadata bit that can be matched on in subsequent match action processing. And the parser can have other states as well. In fact, it's quite common for a P4 programmer to define one state for each type of header that the parser should extract. So in each state, the parser will execute 0 or more statements and then transition to the next state. Well, and we'll see an example of how this works. So the parser for the V1 architecture it obviously takes in the input packet and produces this header struct. So it fills out the headers in the header struct. There's also the user metadata and the standard metadata that pass through this parser and can be used if desired in your P4 program. So at the left on the top, we're showing the packet in declaration defined in core.p4, and it has a number of different methods associated with it that are very useful for implementing the parser. For today, we'll just focus on using the most basic extract method, which allows you to extract a fixed size header from the incoming packet. So at the bottom, we show what an example parser might look like. This is a very simple, just single state parser. So as I mentioned, parsers always start in the start state, and then in this case, it's extracting the Ethernet header from the packet, and then transitions to the accept state. So once it hits the accept state, then the parser is done. So to implement more complicated parsers, we'll often want to use the select statement, and this is used to branch to different states from a particular state. So the select statement has a structure that's very similar to the case statement in C or Java, but it doesn't have the fall-through behavior, meaning that we don't need to use break statements. So in parsers, they often want to branch to different states based on some of the bits that were just parsed from the packet. So for example, here on the left, we show in the parse Ethernet state, after extracting the Ethernet header, we want to either branch to the parse IPv4 state or the accept state based on the value of the ether type field. So I was going to do a coding break, but since I'll have to transition laptops for that, I'll save the coding for the end, and then we'll do that all together at the end. So with P416, let's talk about controls now. So controls are the other P4 programmable elements in an architecture. So they're very similar to C functions, but they don't have loops. In controls, you can declare your variables, you can create your tables, instantiate externs, etc. And this is where the functionality of the control statement, so the control flow of the control blocks, is specified within the apply statement. So when I'm reading control blocks, I like to start with the apply statement. And so with control blocks, we can express all sorts of processing that's expressible as a directed acyclic graph. For example, match action processing, or deparsers, or additional forms of packet processing, for example, updating checksums. So the interfaces between a particular control block and the other blocks in an architecture are governed by user and architecture-defined types, which typically headers and metadata. So here we see an example of a control block. It's very simple. All it does is swap the source and destination MAC addresses and then send the packet back out the same port on which it arrived. So we declare a 48-bit variable called temp, and then temp stores the value of the Ethernet destination address as the swapping is taking place. After the swapping is done, we set the egress spec. We set the egress spec to the ingress port. So hence the name Reflector. And we could also implement the reflector by defining a simple action called swap MAC, and then invoking this action directly from the apply statement, similar to how you might invoke a C function. So actions, they can be declared inside a particular control, or they can be declared globally if you want to reuse them in different control blocks. And since we're invoking this action directly from the apply statement, each of the action parameters must specify explicitly both the type and the direction. And within actions, you can declare variables, as we're doing here, or you can use many different standard arithmetic and logical operators, such as the ones shown here. So tables are really the fundamental unit of a match action pipeline. And they specify what data to match on, as well as the type of match to be performed. A table definition will also specify a list of all possible actions that can be invoked by this table. And a table definition may optionally specify a number of additional table properties, such as the size, so how many entries the table should be allocated to contain, a default action that should be invoked if no match is found within the entries, as well as perhaps some static entries. So each table contains one or more entries. Each of those entries specifies a specific key to match on, and a single action to invoke if a packet matches that specified key, as well as any action data to provide to that action as input parameters when it is invoked. So let's walk through the steps of performing match action processing. So as I mentioned, each table consists of one or more entries, and those tables specify the key, the action ID, and the action data. These entries can be added or removed from the control plane. Each table also specifies a default action ID and default action data. And so when the packet comes in, the table will extract the specified bits from the input headers and metadata to create the key, and then attempt to look up that key within the table entries. So if a match is found within one of the entries, that the action ID and data are read out of the corresponding entry. And if a match is not found, then the default action ID and data are used. So both of these outputs are sent into the multiplexer, which chooses one of these based on whether or not a hit was found in the table. So the selected action ID and action data are sent to the action execution unit. So the action execution unit can use two different types of parameters, two different types of input parameters. So there's the action data that's stored in the table entries itself, but actions can also operate on the headers and metadata. So those are passed along to the action execution unit as well. And your action code will update the headers and metadata as you've defined in your action to do so. So to build our IPv4 router, we'll need to define a table. So we'll need to define a routing table. So in this particular routing table, we see the keys are the destination IP addresses, and we specify a prefix length. So in this particular example, if a packet comes in with destination IP address of 10.0.1.1, then it'll invoke the IPv4 forward action and provide as input to that action the destination address and port number shown here. Similarly, if a packet comes in with a destination IP address of 10.0.1.2, then it will be dropped. So I just want to take a moment to highlight the distinction between the data plane and the control plane. So the data plane, which is described in P4, defines the format of the table. So it's the keys that you're matching on, the actions that can be invoked, the action data, and it performs the actual lookup and executes the chosen action. The control plane, on the other hand, is responsible for populating the table with entries. So there can be many different control mechanisms for adding and removing table entries. But for example, based on network operators, default or manual configuration, or automatic discovery, or routing protocol calculations. But really, both of these planes have to work together to make IP routing work properly. So here's what that routing table that we just described would look like in P4. So as I mentioned, the key is the IPv4 destination address, and we specify a match type of LPM, which stands for longest prefix match. And the possible actions that can be invoked are IPv4 forward, drop, or no action. And we specify that the table should be allocated with enough room for 1,024 entries, and the default action should be no action. So when you define your table, when you specify your table implementation, you specify a particular match type. And tables can have different match types. Core.p4 defines three types that must always be supported by different architectures. And these are the exact match, ternary match, and longest prefix match. And you can also, different architectures can also specify additional match types in addition to these three standard ones. For example, the V1 model defines the range and the selector type as well. So let's talk about actions. So you already saw that actions could be invoked directly from the apply statement. And based on the discussion we just had about tables, you're probably already aware that tables can invoke actions as well. And so as a result, actions have two different types of parameters that can be, that correspond to these two different ways of being invoked. So directional parameters are those that are provided by the data plane. So these are the headers and metadata that come along with the packet. And then there's directionless parameters, which are those that are provided from the control plane. So these are the things that are stored within the table entries itself. And so actions that are called directly only use directional parameters, hence those are provided by the data plane. And actions that are used in tables typically will use directionless parameters, but may also use directional parameters sometimes as well. So after we define what our table should look like, we have to apply it within our control logic. And we do that by invoking the table's apply method, as shown here. It's pretty straightforward. And so the next thing to cover is the deparser. So the deparser is responsible for assembling these headers back into the final packet. And here at the left on the top, we're showing the definition of the packet out extern from core.p4, and this has a method called emit. And this emit method can be used to insert a particular header back into the packet. And it'll only insert that header into the packet if it is valid. And so remember, I said headers have an implicit validity bit associated with it. So as the packet is parsed, that parser will set a packet's validity bit. But you can also explicitly unset the header's validity bit within your P4 program if you'd like as well. Okay. So I'll walk through this, what's going to happen under the hood when you type make. So when you type make, it'll compile your P4 program, launch your mininet topology, and set everything up. So when you type make, each of the switches is running an instance of this simple switch program. And so you write your P4, so the simple switch program, as I said, there's a port interface which connects to the virtual interfaces. in the Linux kernel. And then there's a parser, the ingress pipeline, the traffic manager, the egress pipeline, and deparser, and then it goes back to the port interface. So you write your P4 program, and you run it through the compiler, which produces this JSON file. This JSON file is then loaded into the simple switch program. And you can also attach a simple command line interface to each switch. So each switch is running on a different port. When you run make, it'll tell you which port each switch is running on, and you can connect to that port. And this is useful for like reading the table entries and adding and removing table entries and just generally debugging as you're going along today. So we set up a bunch of virtual interfaces, and each switch is connected to some set of virtual interfaces, and we can send packets through the Linux kernel to the different between the different switches with some packet generator, and then receive the packets with some packet sniffer like Wireshark or Scapy's sniff function. So each switch will also generate some set of logs, which is very useful for debugging. So the logs that are produced will be in the /temp directory. Feel free to check that out if you get stuck and you want to figure out what's going wrong in your P4 program. So to compile the program, you start off with your test.p4, and you compile and produce your JSON file. So this is the command to do that. But this is done in the Makefile, so you don't actually have to do this. I'm just walking through the steps of what the Makefile does. So the second step is to set up the virtual interfaces. And so we create pairs of virtual interfaces and connect them together. And we have to do some things to make sure that the Linux kernel doesn't do anything unexpected as we're testing out. For example, we have to disable the TCP offload engine, and we have to disable IPv6. And to start, and the Makefile will also start up all the models, so we can pass it which ports, which virtual interfaces to connect to, and we can say whether or not we want to generate the logs and whether or not we want to produce the PCAP files. So we can sniff on all of the interfaces, and that allows you to see how the switches are processing packets of both the inputs and the outputs. So to start the command line interface, there's a command, simple switch CLI. You can also pass it a port number as an option. Remember I said each switch is running on a different port, so you just run simple switch CLI to start up that and connect to a particular switch. And once you do connect to the command line interface and you connect to a particular switch, you can type help and see the list of all of the available commands that can be used to debug and figure out what's going on in your table. You can show all the tables that are in the switch, dump table entries, add and remove table entries, and so forth. So for these exercises, we'll be using mostly Scapy. So Python Scapy is a very useful packet generation, packet sniffing tool. It's very flexible. But you could use other things as well. You can use the built-in Linux utilities or Wireshark to do packet sniffing, for example. Okay, so I'm going to switch laptops now, and we're going to go through the implementation of the basic IP router. So let's go ahead and walk through the basic .p4 exercise. So implementing our basic router together. So we're in this is the directory here. We're in the basic directory. So P4D2 2017 fall exercises basic. So if we open up the basic.p4 file, we see, so this file follows the same general structure as the Hello World example that we saw earlier. So at the top, we include core.p4 and v1 model as we did before, and we define a type IPv4, which is the hexadecimal value 800, corresponds to and that we'll be using that in the parser to implement our parser. So that's the ether type of the IPv4. So we've already defined the headers. So the Ethernet header and the IPv4 header for you in the starter code. It's similar to how this is exactly the same as how I showed you in the slides before. We've built the header struct already, so we've included instances of those headers within the header struct. So now we have to implement the parser. So let's start with this. As I said before, the way that I like to do it is I define a different state for each type of header that's being invoked. So we want to parse Ethernet, Yeah, so as I said before, I like to define a different state for each type of header that is being parsed. So we have the start state, the parse Ethernet state, and then we'll also define the parse IPv4 state, parse IPv4. So our packets will always start with the with the Ethernet header. So let's transition to the parse Ethernet state from the start state. So transition to parse Ethernet. Okay. So yeah, from the start state, we're going to transition to the parse Ethernet state. And then within the parse Ethernet state, we will need to extract the Ethernet header. So we do that by invoking the packet in. So packet is an instance of the packet in extern. So it has an extract method associated with it. So we will do packet.extract. And we will extract the Ethernet header, header.ethernet. Okay. So after we've extracted the Ethernet header, we're going to want to examine the Ethernet's ether type field. So the ether type field, and so we'll want to branch to either the parse IPv4 state or the accept state based on the value of this ether type field. So to do that, we will transition select, and we will select on the Ethernet header's ether type field. So Ethernet.ether type. Okay, great. And so if the ether type field is the type IPv4 that we've defined above, so type IPv4, then we want to transition to the parse IPv4 state. So parse IPv4. Otherwise, the default catch-all will be to transition to the accept state, meaning we're done parsing. So default accept. So if the ether type is not type IPv4, then we will just transition to the accept state. And so now we have to implement the parse IPv4 state. So in this state, we're going to want to extract the IPv4 header. So just like we extract the Ethernet header, we will do packet.extract, and it'll be header.IPv4. So you can think of parsers as if there's like a cursor that's, it starts at the beginning of the packet and it moves forward. It can only move in one direction, it only moves forward. And the extract method will look at the next bits of the packet and fill out the header struct that you pass to it with the next bits of the packet corresponding to the size of the header. And so after we've extracted the IPv4 header, then we're just going to transition to accept because we're done. Transition to accept. Okay, so that completes the basic implementation of our IPv4 router. And so now let's take a look at the other blocks that we have to do. We won't do anything with the verified checksum, just for sake of simplicity. And we'll have to finish the implementation of the ingress processing pipeline. The egress pipeline won't have to do anything, so our egress control block will be empty. And then there's a compute checksum block. So remember, our IPv4 router will update the TTL. It'll decrement the TTL. So we're going to need to recompute the IPv4 checksum. And to do that, there's this very convenient extern defined in v1model.p4, which is included at the top of this file. And it's called update checksum. And it's pretty straightforward. You pass it the IPv4 header fields, and you specify which field should be updated. So we're passing it the header checksum field. And you specify the hash algorithm to use. And there's different hash algorithms that are defined in v1model.p4. So we're passing in this csum16. And this extern will update the header, the IPv4 header checksum if the header is valid. And if the header is not valid, i.e. a packet comes in that doesn't have an IPv4 header, then it won't do anything. And we have to implement the deparser. So let's do that really quick because it's pretty easy. So we want to use so packet out now. It was packet in the parser, and now it's of type packet out. So the packet out type has a method called emit associated with it. So to emit the headers, we just do packet.emit. and the header type. So header.ethernet. Header.ethernet. Okay. And we want to emit the packets in the right order, so the order definitely matters here. So after the Ethernet header, we want to emit the IPv4 header. Packet.emit and header.IPv4. Okay, so that's the full implementation of the deparser. And remember I said the emit method will only insert header into the packet if it's valid. So if a packet comes in that doesn't have an Ethernet or doesn't have, well, it'll have an Ethernet because we're extracting it immediately without checking anything. But if a packet comes in that doesn't have an IPv4 header, then the IPv4 header won't be valid, and hence the emit method won't insert it into the packet. So let's look at the ingress control logics. This is the other thing that we have to update. So let's look at the starter code that's provided. So as I said, I like to read the way I like to read control blocks is by starting from the apply statement. So because this is where the control logic is actually defined. So we see that it applies one table called IPv4 LPM, and that table is defined just above here. So this is the exact same table that I showed you in the slides before. It matches based on the destination IP address, and the match type is LPM, which stands for longest prefix match, just like we want. And the actions that can be invoked are IPv4 forward, drop, and no action. The size is 1024 entries, and default action is no action. And so no action is defined in core.p4, it just does nothing, as you can imagine. Drop is defined above, just right here. It invokes this extern called mark2drop, which is also defined in v1model.p4. And so the only thing we have to do is to complete the implementation of the IPv4 forward action. So this action needs to do a number of different things. The first thing that it needs to do is it needs to do routing, or it needs to set the egress spec. So this action will be invoked by the table, and the table will specify the particular destination IP addresses and provide to this action the port number that the packet should go to. And so we need to set the standard metadata dot egress spec. So this is the field that we set to tell the traffic manager which port to send the packet to. Okay, so we've set the egress spec field, and now we need to move the packet's current destination MAC address to the packet's source MAC address. So we'll update the header.ethernet.source address to be the header.ethernet.destination address. Okay, and then we need to make the packet's destination MAC address to be the MAC address that's provided when this action is invoked right here. So this is also something that's stored within the table entries. So to do that, we just do header.ethernet.destination address, and that's equal to the provided destination address. Okay, and remember the last thing that we have to do to complete our... okay. Yeah, so I'll take a little second to pause. Does anyone have any questions about what we've done so far? Great, everything is super clear, and everything is really easy. Oh, there's one question. So no, the egress spec is the field that the traffic manager looks at to figure out which port it should schedule the packet to. The egress port field is read within the egress pipeline. So that can only be read within the egress pipeline. It says the port that the packet is actually departing from. So that's like you can't set that in the ingress port field or ingress pipeline. So let's decrement our TTL. So the header.ipv4.ttl is equal to header.ipv4 minus 1. Okay, so IPv4.ttl, yeah. So that decrements the TTL field. And so at this point, we've completed the implementation of our basic IP router. So let's check and see if it compiles. Oops, that wouldn't have compiled. Okay, so let's check and see if it compiles. We can do that by typing make build. Great, I didn't make any typos, any other typos. Okay, so now let's, if we type make run, or just make, that'll do both build and make run. But if you type make run, then that will it'll launch the Mininet topology with your BMV2 switches that are running your P4 program. And then we have this nice Mininet command line, and we can start up an Xterm, a terminal on host 1 and host 2. Xterm H1 and H2. Great. And so there's a send.py and receive.py. So on host 2, we will run the receive.py function. This is just our really simple Python server. And it's just sniffing packets, and it'll print any packets that arrive. And so on host 1, we want to try to send to host 2. And the way that this utility works is you specify the destination IP address. So this will set the destination IP address in the packet we're sending. So the IP address of host 2 is 10.0.2.2. And we want to, and then we also specify a message. So we'll say that P4 is cool, because you can't deny it. Okay, cool. So it looks like it arrived correctly. It's the Ethernet header, and then the IP header. And let's see if the TTL was decremented. So before we sent it, it was 64, and when it arrives, it was 62, because remember, it's passing through 2 switches in the simple triangle topology. So it looks like it's working properly, and the message is received. That's great. Cool, so things are working properly. So the next thing to do will be to implement the basic, so the next exercise is basic tunneling. I'm wondering how, do you have the slides on here already, Robert, or no? Where's Robert? No? Okay, I think I'll have to switch laptops again. But take a look at the basic tunneling exercise. The README is in the, take a look at the README that's in the exercise. And once I get this set up again, then I will explain it again. But for the next, let's take the next 15 minutes for you guys to work on that, and then at the end we'll come through and we'll implement it again and walk through the implementation of our basic IP router, or basic tunneling exercise. Okay, so I just want to go through the basic tunneling exercise, as far as what you're supposed to do. So in this exercise, we're building directly on top of the IPv4 router, and we want to define a new type called mytunnel, which is used to encapsulate the IP packets. This mytunnel header will contain 2 fields, the proto ID, which just specifies the type of packet being encapsulated, as well as the destination ID. So that's the destination of the host that we're trying to send to. So if a tunneled packet, that is a packet with this mytunnel header, comes into the switch, then we want the switch to forward based on the destination ID field specified in the mytunnel header, and not the IPv4 router, not the IPv4 destination address. So the list of to-dos for this assignment, well, the first and last on this list have already been implemented for you in the starter code. So we've already defined the type, the new header type called mytunnel, and added it to the header struct. So we'll need to update the parser, and we'll need to define a new action called mytunnel forward, a new table called mytunnel exact, and we'll need to update the control flow in the myingress control block. And we'll need to update the deparser. And then we've already provided the rules for you, the table entries for you. And I'll show you where that file is. I just realized I forgot to show you the table entries when we went through the basic router, but I will make sure to do that this time. And so this is the basic topology. It's the same as we had before. This diagram also shows the port numbers for the switches, so we can understand what the table entries are supposed to be. So let's go ahead and walk through this. Okay, so we went from the basic directory to the basic tunnel. So the starter code is in the file called basic tunnel. So the starter code is basically just the solution for the basic IPv4 router. So this file includes core.p4 again. We defined this new type called mytunnel type. So this is the ether type that corresponds, or that we'll use to determine whether or not the packet has a mytunnel header. And then there's the same IPv4 type as well. Oh, we need to change I just realized. What was it? BG. BG colon what? Dark? D-A-R-K? Ah, okay. Ah. Okay, great. Thanks again. Okay. So we've defined the new header type already. MyTunnel consists of the proto ID and the destination ID field that I said already. And then there's and then we added the MyTunnel header to the header struct as well. So we will start by updating the parser logic. So for the parser, we're going to want to define a new state to actually parse our mytunnel header. So let's do that. So the state, we'll call it parse mytunnel. Parse mytunnel. Okay. And in this state, we're going to want to extract the mytunnel header from the packet. So let's do that. So it's the same as how we extracted the Ethernet header and the IPv4 header. So we'll do packet.extract, and it's header.mytunnel. Okay, and then after we've parsed the mytunnel header, first, does this make sense to everyone, what we've done so far? We'll still need to update the parse Ethernet logic to actually transition to the parse mytunnel state. But for now, we're just focusing on the implementation of the parse mytunnel state. So remember, the mytunnel header contains a field called proto ID, and that proto ID field indicates what type of packet is encapsulated within the mytunnel header. And so if the proto ID field is equal to the type IPv4 that we've defined above, then we want to transition to the parse IPv4 state. And so to do this, just like we have done in the past, to transition between two different states, we use the select statement. And so we want to transition, select, and we're selecting based on the mytunnel header's proto ID field. So that's header.mytunnel.proto ID. Okay. So now we're looking at the proto ID field, and we want to, if it's equal to type IPv4, so it's very similar. Take a look at the Ethernet header. So it's going to look exactly like this, actually. Like in this case, in the parse Ethernet header, if the ether type was equal to type IPv4, then we want to transition to the parse IPv4 state. And in the parse mytunnel state, if the mytunnel's proto ID field is equal to this value, then we're going to want to transition to the parse IPv4 state. So let's just type that, type IPv4, and we're going to want to transition to the parse IPv4 state. And the default, so we'll only look at encapsulating IPv4 packets for now. So that's the only type. So if it's anything else, if the proto ID field is anything else, then we want to terminate the parser. We want to be done. So the default will be to transition to accept. Okay. So now we have to update the parse. we're gonna want to update the parse Ethernet state. So if a packet comes in that's not encapsulated, that is, it doesn't have a mytunnel header, then we want it to parse the IPv4 header. So as it is now, this is correct. But we're going to want to add in another condition. So there's two different types that the ether type can be. It can either be type IPv4, or it can be type mytunnel, which is that constant that we defined at the top of this file. So type mytunnel. And we're going to want to transition to the mytunnel state, parse mytunnel. So now we're checking two conditions for the ether type. So if it's mytunnel, then we transition to mytunnel, and otherwise to parse IPv4. So does this make sense to everyone? Are there any questions so far? Okay, great. So this is the full implementation of our updated parser to parse this mytunnel header, or encapsulated in normal IP packets. So now let's take a look at the other things that we will have to do. So we won't, again, do anything with the myVerify checksum block. We'll have to update the logic in the ingress pipeline. We'll do that at the end. And the egress pipeline doesn't have to do anything either, so we'll leave that blank. The compute checksum block isn't doing anything, or it is doing something. It's doing the same thing that we just did in the previous exercise, and we don't have to change it at all, because we don't have to change like the position that the packet is, or that the extern is updating, because we just pass it the IPv4 header checksum field, and so it updates correctly. And so let's do the parser. So the parser, it's going to look very similar. Remember I said that the emit method only will insert a packet into the parser, or into the packet, if it's valid. So we don't have to do any extra checks of validity for the header fields or anything. We can just make this look exactly like the other ones. So we're going to want to emit the header.mytunnel. So in this case, it'll emit the headers in this order. So if a packet comes in that's tunneled, it'll emit the Ethernet header, then the mytunnel header, then the IPv4 header. And if a packet comes in that's not tunneled, then the mytunnel header won't be marked as valid, so that hence the emit method won't actually insert it into the packet. And it'll be exactly like we want the Ethernet header, then the IPv4 header. So this is it for the deparsing logic. Are there any questions about this? If not, then we'll go on to implement or finish the implementation of our ingress logic. Okay. Yeah, so if you wanted to strip, if you didn't want to insert the packets into or headers into the packet, then you just don't emit it. Yeah. Yeah, exactly. If you wanted to emit IPv4, then Ethernet for some reason, then you could do it, you swap the order. So my ingress control logic is exactly how it was in the previous assignment. So nothing's changed here. So we're going to want to define a new table called mytunnel exact, which performs an exact match based on the mytunnel destination address, destination ID field. So let's just make a copy of this table, the LPM table. So for those that are using Vim, if you want to make a copy, you can highlight it and type V, enter visual mode, and then you can type Y for yank, and then you can paste it. So let's update the implementation of this table. So we're going to call it mytunnel exact. Mytunnel exact. Okay, and the key for this table will be the mytunnel header's destination ID field. So let's update this. Header.mytunnel.dstid. And we want to do an exact match. So we specify the type of exact. And then the actions that can be invoked by this table, we don't want to invoke the IPv4 forward action. We're going to invoke a new action that's called myTunnelForward. myTunnelForward. And the other actions are the same as the previous table, so the table could also invoke the drop method or the no action. So does this table declaration make sense to everyone? Everyone's happy with this so far? Great. So we have to define this new action. The action is called myTunnelForward. The point of this action will be to set the egress spec field appropriately so that the traffic manager knows which port to send the packet to. So we'll define the action. It's called action myTunnelForward. Okay, and the input or the parameters that will be provided by the table. Note that the parameters are directionless, and that's because they're invoked by the table. If we were to invoke this action directly from the apply statement, then we would have had to specify the direction of the input of the parameter. But in this case, it's invoked by the table, so it's directionless parameter. So egress spec. This is a type that is defined in V1 model. So the input parameter for this action is the port, and all this action has to do is update the egress spec field. So standard metadata dot egress spec is equal to the provided port number. So this is the field that will tell the traffic manager which port to send the packet to. So it's very similar to how we were setting the egress, or it's exactly the same as how we were setting the egress spec field in the IPv4 forward action. But in this case, we don't have to decrement the TTL or anything because that's not part of our routing protocol for myTunnel headers. We just want to look at the myTunnel header and then perform forwarding based on that and pretty much completely ignore the IPv4 forward header. So now we've defined our new table, we've defined our new action. The only thing that's left to do is to update the control logic. So if the IPv4 header is valid and the myTunnel header is not valid, then, only then, do we want to apply the IPv4 LPM table and perform IP routing. So this is the logical AND operator in P4. And so we want to check if the IPv4 header is valid and the myTunnel header is not valid. So, and not header dot myTunnel dot is valid. Okay. So now we're only performing IP routing if the IPv4 header is valid and the myTunnel header is not valid. And we want to forward based on the myTunnel header only if the myTunnel header is valid. So we can add another if condition in here. So if header dot myTunnel dot is valid. And so if the myTunnel header is valid, then we want to apply the myTunnel exact table that we've just defined. So we'll apply that table, myTunnel exact dot apply. So this will apply that table, and it'll perform the match based on the myTunnel header's destination ID field. And the table entries will specify which action to invoke for different values of the destination ID field. The table entries are specified in a different file. I'll show you that very soon. But so at this point, we've completed the implementation of our basic tunneling example. And I just want to check and make sure I did this. Yes, okay, I did do this. Okay. So we're done with the P4 implementation of our basic IP router. Let's take a look at the table entries. So the table, or the command line arguments, the command lines to add entries to the table are specified in the S1 through S3 commands.txt file. So each switch has a different set of commands to add table entries. So let's look at the commands that are used to populate the table entries for switch 1. So the first line sets the default action of the IPv4 LPM table to drop. These first 4 entries were also specified in the S1-commands.txt file for the basic IP router, but I forgot to show you that. But this is the exact same table entries. So, and the next 3 lines add different entries for different values of the destination IP address. So this says if a packet comes in with destination IP address of 10.0.1.1, then we want to invoke the IPv4 forward action with these parameters. So if you go back and look at the P4 description of the IPv4 forward action, it specifies that there's two parameters that it takes, and that's the destination address and the port number. And so my tunnel table is pretty much the exact same format as that. So we want to specify the default action should be drop, and then we add different table entries for different possible values of the mytunnel header's destination ID field. So this adds 3. So if the packet comes in with destination ID field of 1, then we want to send it to port 1. Destination ID is 2, then we want to send it to port 2. Okay, so let's check and see if our example that we just coded actually compiles. To do that, we type make build. Okay, great, didn't make any typos. So now we can run it. I'll type make this time just to show you that it does the exact same thing. So this compiles the P4 program again and then launches the mininet topology with your BMV2 switches that are described in P4, and we can open up H1 and H2, a terminal on both host 1 and host 2, again, just like we did before. There's the send.py and the receive.py functions again, but these are slightly modified so that they can also send tunneled packets, so they can also send packets with the mytunnel header, which are encapsulating the IPv4 header. So let's run the receive function on host 2. This one's pretty much the exact same. It just sniffs and will print out any packets that are received. And then we want to send. So let's check and see if just normal IP routing is working, make sure we didn't break anything. So to do that, we specify the destination IP address of host 2, which is 10.0.2.2. And we can specify a message again. So P4 is cool. Okay, great. It looks like IP routing is working. The TTL was decremented again. It went from 64 to 62, and it reached the destination host of host 2. So that looks good. So now let's try to send a tunneled packet and see if things will work properly. So to send a tunneled packet, we can use the same utility. So remember that it doesn't look at the destination IP address at all. So we can use whatever we want for the destination IP address. So we'll say 1.2.3. And then we can specify a message of P4 is great in all caps. P $ is great. P4 is great. And then to send a tunneled packet, you specify a destination ID. And the destination ID of host 2 is 2. So we'll send that. And hey, it looks like P4 is great arrived, so the packet arrived. And it is indeed a tunneled packet. So there's the Ethernet header, and the mytunnel header, and then the IP header. And so note that it didn't look at the IP address at all, so it wasn't doing IP routing. It was actually forwarding based on our own custom tunneled header. So that's pretty much the whole exercise at this point.
One thing before we stop I wanted to point out to you is that in the directory structure for the exercises, At the top of every, well, you'll see that in the exercise directory, there's different exercises throughout the day. At the top of every, the top layer of every subdirectory is a README file, and you can take a look at that README file, and it step-by-step describes sort of what that exercise is supposed to do, and also the steps that you need to do to complete the exercise. So if you want to follow along and you miss the slides on the projector, you can just refer to the README file. The other thing to point out, which I'm not sure if you did or not, but every directory also has a solution subdirectory. If you want to cheat, I don't encourage you to cheat, but at the same time, there is a working solution in the solution subdirectory, and you can take a look at that to sort of understand any problems that you may have had if you want to sort of rapidly try and figure out what's going on. Okay?